Welcome to a presentation on evaluating post-hoc XAI approaches through synthetic tabular data. The research area of explainable AI tries to answer the question of how a black box model makes its decisions. In this work, we'll focus on approaches that highlight which features, or pixels in the case of images, were most relevant for a model's prediction. There have been a multitude of approaches introduced over the recent time that do this. We will be focusing on evaluating the 8 approaches that you see on screen right now. Since most of these approaches have been introduced for image data, in this work we will deal with the question of how they perform on categorical tabular data. In a test setting, we will be evaluating XAIs with Boolean functions. That raises the question of what an explanation of a Boolean function looks like. For this, we use the intuition of pivotal elements. That is, if we, for a formula, have an assignment of variables given, then the variable that single-handedly is capable of changing the function output, if it itself is changed, is considered pivotal to the function and therefore most influential to the function output. Following this intuition, we can build truth tables for basic operations such as an AND or an XOR operation, which we can then use to generate more complex explanations. The problem with this assignment here is that we have 2 possible assignments where not a single variable has relevance distributed towards the function, which is problematic because it does not allow us to differentiate between variables that did impact the functions but are not pivotal in that sense, and variables that have no impact on the function whatsoever. Due to this, we add them to the truth tables and consider them both influential in these cases. Using these truth tables, we can then generate explanations for more complex Boolean functions by considering them as Boolean expression trees. We apply our truth tables to every single operation, calculating intermediate results until we arrive at the final function output. As you can see, in this case, the 1 is considered the most influential feature of the function since it alone is capable of changing the function output. With these explanations, we can now create synthetic datasets generating label and explanation from a Boolean function. We also add noise features that XAIs can falsely consider as relevant. Feeding these inputs to model and XAI, we however arrive at a second challenge we need to address. Consider that the outputs given by the XAI do not match our gold standard explanations. In this case, we are still not sure whether the XAI has made a mistake or the model has made a mistake and the XAI has explained it correctly. So therefore, we have to separate model and XAI. We do this by guaranteeing that the model has done its job correctly, so we know that any errors can be attributed to the XAI and not the model making a mistake. We address this in a data generation, creating all permutations exactly once and utilizing a train test split. This allows us to verify that the model generalizes over all permutations not in the training data, showing that the model is capable of generalizing over the entire Boolean function. In our experiments, we use 12 Boolean features, giving us 2 to the power of 12 data samples for each dataset. We employ 5-fold cross-validation, which we repeat 10 times to ensure that the results are not dependent on the train test split. And we use a neural network that achieves 100% accuracy on both train and test set to ensure that the model generalizes over the function and errors are down to the XAI. When evaluating the 8 XAI approaches, we find that even on basic linear AND and OR operations, most XAIs fail to correctly identify the important features for all data samples, with only SHAP and LIME managing to do so. On the nonlinear XOR operation, LIME performs significantly worse. However, this is not unexpected, since LIME assumes data to be locally linearly separable, which is not the case for an XOR operation. So while SHAP still manages to correctly explain all samples, the other XAIs drop in performance significantly. When we evaluate more complex Boolean functions, we find that performance deteriorates heavily, with even SHAP not being able to explain all data points perfectly. We further investigate XAI performance when the problems increase in complexity. For this, we generate 8 datasets with different amounts of features affecting the label, according to the formula seen above. For linear Boolean functions, we find that line performs best, being capable of explaining all data samples for functions with up to 6 relevant features. SHAP also manages to explain a high amount of data samples, while the performance of the other XAIs starts to decline quickly. Repeating this experiment for nonlinear functions, we find that performance of all XAIs deteriorates heavily, with even SHAP struggling to explain functions with more than 3 features involved. We also ask ourselves the question whether our findings apply to realistic data with different sample distributions. We therefore take a setting with realistic data and compare results with our synthetic data equivalent. We use GAN-generated netflow data, where the task is to find whether the flows may or may not occur in real life. For this, we create expert annotations as well as expert explanations. We observe that the GAN may falsely generate data that contains TCP flags, even though the transmission protocol is not set to TCP. We create a synthetic dataset mimicking the expert labels with the Boolean function shown below, and test the XAIs on both the real and synthetic dataset. When comparing the XAI results on synthetic and real data, we observe that the general performance of XAIs matches the results of our experiments. While we observe that Lime performs better on our synthetic data, which we assume to be due to our synthetic data being more evenly distributed, the general performance matches our results, with SHAP yielding considerably better performance than the other XAI approaches. In conclusion, we have evaluated 8 XAIs on categorical data, finding that all XAI approaches struggle with complex Boolean functions as well as heavily nonlinear functions. We also find that the investigated gradient-based approaches perform considerably worse than the perturbation-based approaches in our setting. And most importantly, we find that XAIs rarely give fully correct explanations for all data points, which motivates further research in assessing when explanations generated from XAIs can truly be trusted to support our decisions. For further information on our experiments, I want to direct you to the paper itself. The datasets used in our experiments are available at the link that you'll also find in the description. And lastly, if you have any questions regarding this work, don't hesitate to approach me through the contacts shown on screen. Thank you very much for watching.